Hey everyone, it's Mr. Kabbalah. This is going to be a statistics lesson on Unit 8, Section 1 on estimation and estimating mu when you know the standard deviation. So enjoy. Let me know if you have any questions.
All right, so this is Unit 8, Section 1, estimating mu when sigma is known, or estimating the mean when the standard deviation is known. So assumptions we can make about a random variable x. We can take simple random samples of size n from a population of x values. The value of the standard deviation is known. If x is normally distributed, then our methods will work for any sample size n. If x has an unknown distribution, we need a sample size of n greater than or equal to 30, but again, the 30 might depend on the skewness of the distribution. A point estimate of a population parameter is an estimate of the parameter using a single number. X bar, or a sample mean, is the point estimate for mu, the population mean. So we use the sample mean as an estimation for the population mean. Because a point estimate most likely isn't exactly equal to the population parameter, we can calculate what is called the margin of error. This is calculated by taking the magnitude of the difference between the sample point estimate and the true population parameter, and magnitude is another way to say absolute value. So when using x bar as a point estimate for mu, the margin of error is the absolute value of x bar minus mu. So the difference between the two, you kind of get rid of the negative. Because mu is unknown, we cannot calculate exactly how close or far x bar is to mu, so we use what are called confidence levels. To measure the reliability of an estimate. We can use any number that we want between 0 and 1 as like a percentage, or 0% and 100%. But we typically use things like 0.90, 90%, 95%, 99%. In each case, we call this a ZC, which is the number such that the area under the standard normal curve falling between the negative and the positive is equal to C, the confidence level. The value ZC is called the critical value. So it's a z-score, it's just a specific z-score. So what we're going to do, depending on how confident we want to be, we're going to need different z-scores for the area. So I'm going to be using my calculator and the inverse normal function to get these. So if we want a level of confidence of 70%, so we're talking about this area under the curve. All right, so what we're looking for is a negative z here and a z here. Now 70% is what we're looking for. What we need to tell the calculator is to calculate this section and this section, or basically find this point. So 70%, if what's remaining on the left and the right, so there's 100 minus 70 is 30. So there's 30% underneath the curve for this area and this area, and it's going to be split equally. So that 30, if we divide by 2, that means 15% here and 15% here. So what I'm going to tell my calculator to do is I'm going to do the inverse normal, so second vars. This is choice number 3. And because it's 15% on the left and the right, I'm going to put in 0.15. The mu is still 0. Sigma is 1. And this is going to tell me the critical value if we want a 70% confidence level. So it's negative and positive 1.04. So negative 1.04 and positive 1.04. And we can do this for any level that we want. So 75% would be a little further out. If we do 100 minus 75, that's 25% left for both the left and the right. So 12.5% here and 12.5% here, 75 here. So on my calculator, I'm going to type in the area as being 0.125, changing that 12.5% to a decimal. Now I'm going to start doing the picture and the z-scores for all of these. I'm going to maybe speed up the video so it doesn't take too long. But essentially it's the same process over and over again, just with different percentages. So I'm going to just keep going, and then at the end we'll fill in a table. All right, so if we did that, then at 70%, we have 1.04, and I'm only going to do the positive value. 75 was 1.15, 80% was 1.28, 85% 1.44, 90% 1.65 or 645, 1.96, 2.33, and 2.58. Another computation that is important to confidence levels and critical values is finding the maximal margin of error, or error tolerance. So how much error are we willing to tolerate? And there's a computation. Basically, to find E, the error tolerance, we take that critical value, the ones that we just calculated, and we're going to multiply by, if you remember, the standard deviation for a sample mean distribution or an X-bar distribution is this standard deviation divided by the square root of the sample size. So basically it's the standard deviation. So this part here is the standard deviation I'll use of the X-bar distribution. And then that's multiplied by the critical value Z. So the probability that our true population mean mu is between the sample mean minus the error tolerance and the sample mean plus the error tolerance is equal to our confidence level. So we call this the C confidence level, or interval, because it's going to be an interval for mu. This is an interval computed from sample data in such a way that C is the probability of generating an interval containing the actual value of mu. In other words, C is a proportion of confidence intervals that actually contain that mean. So here's an example. Julie enjoys jogging. She has been jogging over a period of several years. She usually jogs around 2 miles per day. Standard deviation of her times is 1.80 minutes. During the past year, Julie has recorded times to run 2 miles. She took a random sample of 90 of these times. For these 90 times, the mean was 15.60 minutes. Mu is the population mean jogging time. So find a 95% confidence interval for mu. So what we're going to do is we're going to first figure out the error tolerance. which is going to be, now since we want a 95% confidence interval, then our critical value ZC is going to be 1.96. Okay, if you want to go back to the table that we made, here just to show you where I got that, 1.96 right there. Okay, and we're going to then multiply that times the standard deviation, which is 1.80, divided by the square root of the sample size, which I believe is 90. All right, so if we do that on our calculator, so I'm going to do 10 1.96. I get an error tolerance of 0.37. So the interval is going to be the sample mean 15.60 plus that, and then 15.60 minus that. So this is 15.97. This is 15.23. So what this means is that we can be 95% sure that the actual population mean of her running times is between these two. So it probably isn't 15.6, but it might be, but we can be 95% sure that it's within those two numbers. Now, another way to visualize confidence intervals, just to draw a little picture, imagine this line right here as being our population mean. We don't know what it is, but it's there. Now, when we find confidence intervals, I'm going to draw 10 of them. 9 of them are going to actually contain that mu. So there's 2, 3, 4, 5, 6. Now, I'm going to make this one not 7, 8, 9, 10. So that's 9 out of 10, which is a 90%. So another way to visualize it is that we have all of these intervals. 9 out of 10 of them contain that sample mean, or I'm sorry, that population mean. And to the left is the X bar minus E. And then over here is that X bar plus E. Okay, so that's kind of what it's saying, is that 90% of the confidence intervals between these two will contain that population mean. Walter usually meets Julie at the track to run. He prefers to jog 3 miles, show off. From long experience, he knows that his standard deviation is 2.4 minutes for his jogging times. For a random sample of 90 jogging sessions, the mean time was 22.5 minutes. Mu is the population mean. Find a 99% confidence interval for mu. So we're going to first calculate the error tolerance. So the critical value here, if you go back to that chart, 99% would be a ZC score of 2.58. All right, the standard deviation is 2.40, and it's the square root of 90. All right, so we're going to get our error tolerance in a moment, 2.58. Oh, let me start again. So we're talking plus or minus 0.65. So if we take his sample mean of 22.50, subtract 0.65, so 23.15, and 21.85. We can be 99% sure that the population mean is between those two values. All right, 30 small communities in New York, populations near 10,000 each. Now, just so we know that 30 is going to be our sample size, not the 10,000. So just be aware of that. Average of X bar equals 138.5 reported cases of larceny per year. Assume that sigma, or standard deviation, is known to be 42.6 cases per year. So we're going to find a 90% confidence interval and then the margin of error. So again, margin of error is another word for error tolerance. So let's do that. We got an error tolerance of 90%. If you go back to that table, 1.65 times 42.6 divided by the square root of 30. So 42.6 divided by square root 30 times. So our margin of error is about 12.8, and then our interval would be 138.5 plus that, and then 138.5 minus that. All right, so to finalize that, 138.5 plus 151.3 and 125.7. All right, kind of a similar thing here. We're going to do 95%. So 95, the z-score is 1.96. And then 42.6 divided by the square root of 30. And I might zoom it's basically the same calculations, just with a different ZC here and here. For 99%, we're going to see that it's 2.58. 42.6 square root of 30. So note that as the confidence levels increase, the margins of error also increase. And also, as the confidence levels increase, the confidence intervals increase. And it goes back to those drawings we did for those z-scores, that the higher the percentage, the more and more of the standard normal curve you're talking about. So that just kind of makes sense. The z-scores get kind of spread out. So everything, I wrote intervals. I meant increase. Sorry about that. Increase. So another exercise. Type of hummingbird called Allen's hummingbird has been studied by zoologists. A small group of 15 Allen's hummingbirds has been under. They might have had a typo here. The average weight for these birds is X bar equals 3.15 grams. Based on previous studies, we can assume that the weights of Allen's hummingbirds have a normal distribution with a standard deviation of 0.33 grams. Find an 80% confidence interval for the average weights of Allen's hummingbirds studied in the region. What does this tell us? So we're going to need our error tolerance. So an 80%, again, if you want to go back to that table, is a 1.28 ZC score, or Z-score. Our standard deviation is 0.33, and we're going to divide by the square root of 15. Now, even though we don't have more than 30, it does say that it's a normal distribution, so we don't have to worry about that. All right, so calculating it, we get 0.33 divided by square root 15 times, so 0.11. So that means that our interval would be 3.15, that's x bar, minus 0.11, and then 3.15 plus 0.11. So that would give us, what is that, 3.04 through 3.26. So what does that tell us? We are 80% sure or confident that mu is between 3.04 grams and 3.26 grams. All right, so when designing statistical research projects, it is a good idea to decide on the confidence level you wish to use and select the maximum margin of error, E, you want for your project. In order to do this, you'll need to determine the appropriate sample size, N. So kind of adjusting that E equals ZC times sigma divided by square root of N. If we do a little algebra with that, we can change it into N. The sample size is ZC times the standard deviation divided by the error level that we want, and then all of that squared. And then if N isn't a whole number, we typically bump it up to the next largest. And like I said, if it's more than 30 or more, it's pretty standard. You can use a standard normal curve with a sample standard deviation of S. So anyway, to show you an example, a wildlife study is designed to find the mean weight of salmon caught by an Alaskan fishing company. A preliminary study of a random sample of 50 salmon showed S, the sample standard deviation, to be 2.15 pounds. How large of a sample should be taken to be 99% confident that the sample mean X bar is within 0.20 pounds of the true mean weight mu? So we need a couple of things here. We need a ZC score. So at 99%, that would need to be 2.58. We need our standard deviation, which we're going to call S in this case, which is about 2.15. Our level of error, or our maximal level of error, is 0.2 pounds. And that's what we need to find the sample size that we need. So N is equal to, and I'm just going right from the formula, 2.58 times 2.15 divided by 0.2, all of that squared. We do that on our calculator. Divided by, and we get 769.2. But like we just said, anything that's not a whole number, we round up. So we would probably need to take 770 salmon in order to be 99% confident that we have a interval that contains mu. And then I believe this is the last one. This is the Allen's hummingbird again, but this time I'm going to skip down to the end. Find the sample size necessary for 80% confidence level with a maximal error of estimate E equals 0.08 for the mean weights of hummingbirds. So again, we need the ZC score would be at 80%, we're looking at 1.28. The the standard deviation is 0.33, and the maximal level of error estimate is 0.08. So plugging that in, we get 1.28 times 0.33 divided by 0.08, all of that squared. So the number in our sample should be 27.87, which we would round to 28. Okay, that's the end of section 1. Let me know if you have any questions. Hope to see you soon.